Hello, and welcome back to CS 11737. Today I'm going to be talking about dependency parsing. So dependency parsing is a way of analyzing linguistic structure of sentences in a particular language. And there's essentially two ways of performing this analysis. Dependency parsing focuses on relations between words, and basically what we get is a graph structure like this, where we have particular words, and then we have arrows pointing between the words from the head to the dependent. There's also phrase structure analysis, which focuses on the structure of the sentences, and it looks a little bit like this, where we have parts of speech and phrases such as noun phrase, a girl, or with a telescope being a prepositional phrase, etc. So in this multilingual class, I'm going to mainly talk about dependencies. And there's a couple reasons why I'm choosing to do dependencies instead of phrase structure. The first reason why is because they demonstrate the relationship between words in a relatively straightforward way. So for example, we have saw pointing to I, where we have n subj, which basically means that I is the subject of saw. And we see saw pointing to with the label prep, which is saying this is a prepositional phrase. But another reason why I'm doing dependencies instead of phrase structures, they're particularly good for multilingual settings. And one of the reasons why this is the case is phrase structure can be hard to define in languages with freer word order or assumptions other than that of English. So now I feel that when we talk about the analysis of the structure of sentences, we very often talk about dependencies when we're talking about things to analyze across many different languages. A very strong driver of the research into cross-lingual syntactic structure is the Universal Dependencies Treebank. And we've already talked about this in our part of speech tagging class, so I think everybody is familiar with this. But it also defines a standard format for parse trees, specifically dependency trees in many different languages. So I'm not going to go into the details of the exact rules behind dependencies, but one important thing to know is essentially they're trees between languages where we have heads pointing to their dependents, and also there's multiple ways that you can define these dependencies. We can define them either syntactically or semantically. So the Universal Dependencies Treebanks take a semantic approach where essentially the goal is to have semantically related words close together. There's also something called the Surface Syntactic Universal Dependencies Treebank, which has a definition that's a little bit closer to what we expect according to the rules of syntax in languages. And you can see that actually these two different ways of writing dependencies are very, very different, where the one on the left is a little bit deeper. It also more accurately reflects kind of the phrase structure. So this is here is a verb phrase. And this verb phrase is all kind of one subtree rooted in its verb is. Whereas if we have the standard UD treebank formalism, then one would be the head of this. And we have this kind of very flat tree structure over here. So which one you want kind of depends on what you want to use these things for. If you want to use them for semantic tasks like question answering or things like that, you might want to consider this semantic formalism over here. But in my particular case, I tend to be interested in syntax and language structure, so I will be using examples from this SUD over here for the rest of the slides. So one interesting thing that you can get from dependencies kind of immediately is that there are cross-lingual differences in the structure of sentences. And there's a tree bank called the Parallel UD tree bank, and I put some example links at the bottom of the slide here if you want to take a look. But we have an example from English. The sentence, "The new spending is fueled by Clinton's large bank account." And what we can see is kind of the root of the sentence here. We have a noun phrase, "the new spending," on the left side of the root, indicating that this is kind of the subject, and you can even see subject written down here. Then we have the object, it is fueled, and then the prepositional phrase which follows this, this object over here. So what we can see from this immediately is we have our verb up here, and then we have our subject on the left and our object on the right, which tells you that English has SVO word order. And not every sentence in English is going to be like this, of course, but if you take them on the aggregate, you'll be able to see that this structure is very, very common. On the other hand, let's take a look at the same sentence in Hindi. And in Hindi, Hindi is a verb final language. And what we can see over here is we can see the verbs are over here, and then we have phrases over here. And this one corresponds to essentially fueled by Clinton's large bank account. And this one over here corresponds to the spending. So you can see that Hindi instead would be, essentially the verb on the right and the subjects and objects on the left. And then if we look at Arabic, Arabic is a verb initial language, and we can see the subject and the object come on the right. So this is basically VSO word order. So that's the interesting thing. I cannot read Hindi or Arabic, but I can look at these trees and basically say that, oh, I see that the underlying structure of the languages is different just by looking at the analyses here. Okay, so I talked about basically what dependency parsing is on a kind of very high level. And then the next question is, there are not too many people who are interested in looking directly at the dependency trees. So unlike, a machine translation system where there are many, many people who could use translation outputs, or a question answering system where there are many people who ask questions and want answers to them. So what exactly can we do with these dependencies or syntactic analyses of sentences? So kind of on a high level, previously in NLP, before we started using neural network models profusely, these dependencies were used for feature engineering in systems. So we would use these to extract the features that we would then use to perform some sort of downstream question answering or text classification or whatever other task. And they're still useful in some cases for model building as well. But my impression is that at the present, they're more useful for kind of human-facing applications where we use the dependencies to make it easy to analyze some other aspect of the language that we're interested in. And I actually wanted to get some interesting examples of this. So a bit earlier, I asked on Twitter for some examples of what dependency parsing could be useful for. And if you follow this link down here, which will also be in the slides, you can go take a look and see some of the interesting answers that people have given. I'm just going to outline some examples here, and there's many, many more in this Twitter thread. So the first example is adding inductive bias to neural models. And so basically what we would do is we would use syntax in order to inform our neural models to get them to act more consistently or generalize better to out-of-domain data, et cetera, et cetera. So this is an example of linguistically informed self-attention that was used for the task of semantic role labeling. And essentially what this model does is it takes a self-attention model, like the transformer model that we've talked about previously, and it supervises one of the attention heads to try to make that attention head follow dependency structure. So that's what this syntactically informed self-attention here is. And the basic idea why we would want to do something like this is kind of twofold. The first reason is to ensure that the attention itself is passing information along dependency paths. And this will essentially try to make the model follow the syntactic structure when it's combining information to be used for whatever downstream task you want to apply it to, which ideally, if this structure is accurate, would allow you to generalize better and, for example, on data that you haven't seen before in your training data. Another reason is that this gives an additional training signal to the model in that the model has to predict the dependencies at the same time as it's predicting its other objective. And as we've talked about before, multitask learning is a good way to essentially get models to learn better because it makes them, tackle multiple tasks at the same time and learn appropriate feature representations that can tackle both tasks. So that was one example of how we can use it in model building. So another thing that we could use dependencies for is understanding the underlying structure of languages or the underlying syntax of languages. So this is a recent paper by my group where we essentially try to extract syntactic rules about the language based on dependency syntax. And specifically, we focus on morphological agreement rules. These morphological agreement rules are basically saying whether two words need to agree on a particular morphological feature based on the fact that they are in a particular dependency relation. So to give an example from English, in English, we know that subjects and verbs need to agree with respect to numbers. So I am, you are, it is, for example. And English is a relatively morphologically poor language, but in morphologically rich languages, we might have many, many more of these rules. And knowing about these rules is interesting for linguists or language learners, etc. And so what we do in this paper is we essentially use the dependency trees, which could tell us things like this word is the subject of this noun is the subject of this verb. We extract examples from here and we try to discover the underlying rules of morphological agreement in the language that we're interested in. Another example of something that you could do with dependencies is searching over corpora to find kind of interesting phenomena that you would like to know for further analysis. So this is an example of syntactic search over corpora. So let's say you wanted to find an example of where a person was a founder of a particular organization. And so we list this founder, and we have an example of this being something like Paul. And we have was a founder of a particular entity. Let's say that entity is Microsoft. And by using dependency structure, it basically compiles this into a n-subj, n-mod relationship here. And it tries to find all patterns where we have this word, and then we have the noun subject and the noun modifier. And it comes up with all of these examples here. And the reason why this is nice is because there wouldn't be a very easy way for you to express this in, for example, a simple pattern matching thing without knowing the syntactic structure of the underlying corpus, basically. And finally, dependency parsers could be used for analysis of other linguistic phenomena. So as just one example of this, there's a paper examining film scripts, and it's examining power and agency. So in this example, the man with the roses beckons Irene forward, and we have, in this case, power. So beckon is an indicator of positive power for the subject and negative power for the object. So essentially, this allows you to do interesting analysis of film scripts and do kind of diachronic analysis where you examine them over time, et cetera, et cetera. So as you can see, dependency parsers or syntactic structure in general kind of allows us to come up with very intuitive ways of analyzing text and finding interesting things from it. So, of course, in order to do this, we need to have this dependency structure, and there's two ways we can get this. We can annotate it manually, which is, of course, lots and lots of work, or we can try to predict it automatically. And I'll be talking about methods for automatic prediction of dependency structure next. So parsing is essentially predicting linguistic structure from the input sentence. And there's kind of two major methods for how we can do this. First one is a transition-based method, which we step through actions one by one until we have an output. And also graph-based methods, where we essentially calculate the probability of each edge or constituent and then perform some sort of dynamic programming. So previously, when we were talking about part of speech tagging or sequence labeling, we talked about history-based models, where we essentially have a encoder-decoder that tries to predict the outputs one by one, or CRF-based models, where we kind of do a dynamic program over the output. And transition-based models and graph-based models are kind of the analogs to these two ways of performing sequence labeling, except with respect to parsing. So first I'm going to talk about shift-reduce parsing. So shift-reduce parsing basically steps through the sentence one by one and tries to predict actions that will result in edges. And we process the words one by one, left to right, using two data structures. The first is a queue of unprocessed words. The second is a stack of partially processed words. And at each point, we choose to either shift, moving one word from the queue to the stack, reduce left, which takes the top word of the stack and makes it the head of the second word, and reduce right, which takes the second word of the stack and makes it the head of the top word. And we learn how to do each, choose which action we use with a classifier. So this is all very abstract, so let me give an example. We have a sentence, I saw a girl, so we first put this all into the queue or buffer. Sorry, I'm a little bit inconsistent in the wording here. We can call it the queue or the buffer. And we then take actions. So first we shift, and we shift I onto the stack. So now I is no longer on the buffer, it's on the stack. We shift again, so we get saw. And then, sorry, we don't shift, we do reduce left. So basically what this does is this takes saw and it makes the I here be a child of the word saw. Then we shift again. We shift again, so now we have all of our words on the stack. We reduce left, which means we make the left word a child of the right word on top of the stack. We reduce right, which means we make the right stack element. So we had girl and saw, and we make girl a child of saw. And then we reduce right, so we make saw a child of the root, and we're done parsing. So basically, we see that if we choose particular actions, we will be able to get a tree over all of these words in the original sentence. So in order to perform shift-reduce parsing, we need to perform classification. And the way we do so is given a configuration, we need to choose which action we will do. And based on this choice, we'll get a new configuration. So if we shift, in this case, we would move girl from the buffer to the stack. If we predict reduce left, we will make saw a child of A. And if we reduce right, we will make A a child of saw. So there's any number of ways we could perform this kind of classification decision. This figure here is an example of a method called the stack recurrent neural network. And what it does essentially is it encodes the stack, the buffer, and the previous actions, all with 3 recurrent neural networks. And then it uses the encodings for all of these to make a decision over shift, reduce left, and reduce right. So I'm going to go over this briefly because we don't want to, I don't want to go into too many details here. If you want, you can take a look at the paper on stack recurrent neural networks. But basically the idea is we feed in this null symbol here, we feed in n, which is the second to top element on the stack, and then we feed in a representation of this tree, which is encoded using a tree-structured neural network to get the top element on the stack. We feed in the words in reverse order, so we have made and was being the words that we haven't processed yet, and then we feed in the actions that we have done already into a recurrent neural network separately. So we call these state embeddings, and we can embed words using standard word embeddings. We can embed tree fragments using something called syntactic composition. And the contents of the buffer are just a sequence of embedded words, which we periodically shift from. The contents of the stack are a sequence of embedded trees, which we periodically pop from and push to. And because these are sequences, we can use RNNs to get an encoding of them. So basically, the basic idea here, while eliding some of the details, is that we can use RNNs to get the encodings that we use to make these classification decisions. So next, I am going to go to graph-based parsing. Graph-based parsing is perhaps a bit more popular now than transition-based parsing, although they've kind of become more and less popular over the course of history. So who knows where we'll be at in 2 years or so. But basically, first-order graph-based dependency parsing, the way it works is we express every sentence is a fully connected directed graph. So basically between all of the words in the sentence, we have arrows pointing in both directions. Then we have some way of scoring the edges, which I'll talk about in a second. But basically what this tries to do is this tries to score the edges based on the likelihood of them being actually existent in the tree, the final dependency tree. So, a very likely edge, like going from is as the head to this as the child, would have a very high score, and a very unlikely edge would have a very low score. And then we find the maximal spanning tree, which is basically the tree with the highest scores. So in this case, it would be is being the root, and then this, in example, being the children. So this is an alternative way of performing parsing. And why would we want to pick one over the other? So basically, transition-based parsing, one of the advantages of it is we can easily condition on infinite tree context. So we can, use any structured prediction algorithm to encode all of or any sequence encoder to encode all of our previous context. It could be an RNN or a transformer, and basically condition our next decision on all of the contexts that we've seen before. There's a couple issues. One is that the greedy search algorithm can cause short-term mistakes. So basically, it has been found that transition-based algorithms tend to, kind of miss the forest for the trees. They tend to make short-term decisions without being able to model long-term dependencies as well, for example. Although with recent neural models, the difference between the methods is reduced a little bit. Graph-based parsers, on the other hand, can find an exact best global solution via dynamic programming algorithms, but they have to make local independence assumptions. So we can't take advantage of the fact that, because this other dependency somewhere else in the dependency tree exists, then this dependency is more likely to occur because all of the edges are scored independently. So that's kind of a view of the pros and cons of each of these methods. So one thing I said before when I was describing graph-based algorithms is that we find the minimum or maximal score spanning tree of all of the nodes and edges. So there's several algorithms about how to do this. One example of this is the Chu-Liu-Edmonds algorithm. And I'll go through this relatively quickly because the details are not super important, but basically we have a graph and we want to find its spanning tree. And so what we do is we greedily select the best incoming edge to each node and subtract its score from all incoming edges. If there are any cycles, select a cycle and contract it into a single node. Recursively call the algorithm on the graph with the contracted node, and then expand the contracted node, deleting an edge from the overall graph appropriately. So here's an example. Book that flight. So in this case, we first find the best incoming edge to each node. And here, route going to book is the best incoming edge, but that in flight both have each other as the best incoming edge, so we have a cycle here. We subtract the max for each edge from the scores. We contract the node into that flight here. We recursively call the algorithm. And then we expand the edge and we delete the edge that would have been conflicting with the kind of recursively called algorithm here. And we get this, this final tree. So anyway, this is an algorithm that we can apply to graphs to get the best scoring spanning tree. So then the second question is how we actually calculate these pairwise scores. And there's kind of two elements to this. Now, like just about everything else, we use neural networks to learn our models. And in the case of dependency parsing, we run a neural sequence model over the sentence we would like to parse, and we extract features. And we can put them into some sort of multi-layer perceptron, for example, to calculate a score between the words, and that would become our score. So this is the kind of original way that was proposed to do graph-based parsing with neural networks. But more recently, this method of using something called the BiAffine classifier is kind of more widely used. And so the way this works is we have representations of the words, and we calculate the representations of the words with respect to their representation when they're a dependent or their representation when they're ahead. And this is kind of important because each word might kind of play a different role when it's acting as a dependent or ahead. And then we calculate the score of each arc, where we essentially have two ways. We have two ways of scoring the arc. The first one is pairwise between the head and the dependent. And this is basically saying how compatible are this head word and dependent word. And another thing is just calculating the likelihood of a word being a head in the first place. So for example, in syntactic dependencies, in semantic dependencies, it's much more likely for content words to be heads than function words. So content words should get a higher score on average, and the second term kind of allows you to do this. How we train this model, basically we train this model as a classifier over the head word of each dependent. So each dependent has a single head word, and so we train a classifier to try to maximize the probability of getting the correct head. And so basically it's making a local decision and then predicting the overall global tree at the very end. Notably, this has given very good results with careful parameter tuning, but nonetheless good results on the universal dependencies parsing shared task, and it's kind of a standard method in this field now. So this was your brief overview of dependency parsing, what it's used for, how it's interesting as a task. And finally, I'd like to give just a few examples of multilingual dependency parsing. And multilingual dependency parsing is particularly interesting as a multilingual task because it's particularly hard. And why is it particularly hard? Number one, it's on a global level, not just a word-by-word level. So for example, in contrast, named entity recognition, you don't really need to have a global view of the sentence in order to do quite well on named entity recognition. But in contrast, to do well on dependency parsing, you really kind of do need to process the whole sentence as a whole and resolve discrepancies between conflicting interpretations of the sentence. Another thing is syntax varies widely across different languages, like I just showed before with the example of English, Hindi, and Arabic. So there have been a number of methods to propose to improve dependency parsing, and all of these will be potential things that you can do for the reading in class to discuss in class this time. So the first one is order-insensitive encoders. So the standard way of kind of applying dependency parsers to very low resource languages where we don't have a lot of data is to train them on one language and then apply them on another language, either with a small amount or very little data in that language. However, one of the issues is that cross-lingual transfer can fail when we're trying to transfer to very distant languages. And to give an example of this, this paper, which is a very interesting one, did an analysis where they essentially measured how similar languages were and showed that indeed the dependency parsing accuracy with cross-lingual transfer dropped off significantly when you were trying to transfer to more distant languages. So one method that this paper proposed to resolve this issue was to change the model structure. So the underlying model structure is less sensitive to word order. And an interesting result that they found was that both when you use the encoder and the decoder, if you have the most similar languages to English, you have a small drop in accuracy when you have an order-insensitive decoder or encoder. So one example of the order-insensitive decoder is that the BiAffine parser is actually less sensitive to order than the transition-based decoder that I talked about before. However, if you're transferring to very different languages, so if you're transferring, like, for example, from English to Japanese instead of English to Norwegian, the order-insensitive models do much, much better because the underlying word order of the language you're transferring to is very, very different. So another example of an improvement that you can do to improve by cross-lingual dependency parsing is the use of a generative model that can be trained unsupervised. And the idea here basically is we train this generative model on the language that we are transferring from, say English, but then we take it to another language, for example, in this case, Chinese. And Chinese, has syntactic features that are quite different from those of English. So what we do is we take this generative model and train it in an unsupervised fashion to maximize the likelihood of this output in another language. And this is interesting because we're not just taking, an English model and applying it to Chinese. We're taking an English model, we're seeding a Chinese model with this English model, and then we're fine-tuning the model to further adapt to Chinese. And interestingly, this can give us pretty significant improvements, even with no training data in the language that we're interested in parsing. So finally, an example way we can improve dependency parsing accuracy on a low resource language is adding constraints based on our a priori knowledge of the language structure. So the basic idea is that linguists, even if we don't have very much data for particular languages, many linguists might have documented the basic underlying word order of the language in databases like WALS, which I believe we've talked about before in this class. So the idea behind this paper here is essentially that if we look over the whole corpus, and if WALS says that we should have adp noun arcs in Hindi should be more likely to be on the right, and we have this kind of ambiguous structure here where we have noun, adp, noun. This will then decide that we should put the arc facing to the right instead of the arc facing to the left. And they have a nice formulation where essentially they enforce this constraint not over individual sentences, but over the whole corpus. And the reason why this is important is because individual sentences might violate these linguistic rules, but on the whole corpus as a whole, we should see these rules hold more often than not. So this is a very interesting idea that might have applications beyond even just dependency parsing. So as I just mentioned before, our discussion this time is to read these papers that I just introduced. You can read at least one of them. You can read all three of them if you think it's interesting. And we'll discuss where we expect them to work, where we expect them not to work, and if you have any ideas for how to further improve over these underlying methods. So thank you very much. That's all I have for today.